Hello, I'm Melissa Illingworth, and this is my video for Cal Poly on thermodynamics. So the students have just done a few different warm-up questions about enthalpy and entropy. So just to review about enthalpy, we actually had a few different ways we could calculate it. And enthalpy is, for our class, a measure of how much heat energy is being transferred. So we could actually find it using a temperature change. So we had something like mc delta T, a temperature change, the specific heat of the reaction that's happening, and then the mass of everything that's being heated up. And that we set equal to N, the moles of our reaction that was happening, and then now the enthalpy of that reaction. So we could actually use a temperature change to calculate enthalpy of a reaction. Another way we can calculate enthalpy is using a standard thermodynamics table, and that uses heat of formation values, and again the products minus the reactants. So there are two different ways we can actually calculate enthalpy. And enthalpy could have two different possible signs, either positive or negative. And if we have an enthalpy of a reaction that is negative, then this is exothermic, it's heat releasing, and we would call this a favorable reaction in terms of enthalpy. For entropy, we can measure this in the term of microstates. The number of possible states that the atoms and molecules can be in. And in a reaction, we could use, again, a standard thermodynamics table to calculate a change in entropy for a reaction. And also, we could just sometimes look at a reaction, its phases of matter, the number of moles of gas as reactants and products to determine entropy change. And for a reaction, if the change in entropy is positive, if there's an increase in microstates, we would also call that favorable. Okay, so there are enthalpy and entropy. So let's take a look at a reaction now, where we have an example reaction where the enthalpy is negative, but also the entropy is negative. And then I would ask the students to talk to the people around them for a minute or two. Would or could this reaction be spontaneous? And I would expect maybe a few different types of responses. Something like, no, it wouldn't be spontaneous. Something like, it could possibly be spontaneous under different conditions. So let's put some specifics to this. There's a specific reaction that I had in mind for when these two conditions are met. So here, with water freezing, with water going from liquid to solid, what is the sign of enthalpy? What is the sign of entropy? And again, could this reaction be spontaneous? So enthalpy, delta H, that is negative. So for water to freeze, we know that it is giving up thermal energy. The ice, water molecules in solid form have less thermal energy there. And the sign of entropy, the number of microstates, so microstates are decreasing, so we also call this a negative change in entropy. So now, what's going on with this reaction? When is it not spontaneous? So we know that it has to do with the temperature, and specifically low temperatures, to give us a spontaneous reaction. So it's not just enthalpy and entropy that's determining maybe when a reaction is going to happen or whether it will be favorable or will proceed, but also the temperature. So it's both enthalpy and entropy and temperature, actually all three of those, that then tells us about whether a reaction is going to be spontaneous or not. And all of those things are combined in a new term that has to deal with all of them, called Gibbs free energy. So all of these things, enthalpy, entropy, and entropy, all go into determining whether a reaction could be spontaneous. And here's our equation that relates these all mathematically. So here's our enthalpy, entropy, and temperature. And they all go into determining this other change for a reaction, delta G, Gibbs free energy. For this reaction, our temperature will be in Kelvin units, which will mean temperature is always positive. And then for our class, we're assuming that all of the energy that has been transferred is going to be in the terms of thermal energy, that there's no mechanical work done. We have a constant temperature and pressure. So delta G is actually linked to spontaneity. And it takes this delta H and delta S and temperature into account to determine spontaneity. First, I'm just going to show to you how they are exactly linked to spontaneity. So here is our starting reaction, the free energy equation. The change in energy of free energy of the system is related to the enthalpy of the system, the temperature, and then the entropy change of the system. So then to take all of that and then divide each term by negative delta T, here we get then this term on this side of the equal sign. And this is something that we talked about when we were talking about entropy. We have system and surroundings, and the change in entropy of surroundings is related to the enthalpy. So we substitute that particular equation in to get this. So our change in delta G of the system and the temperature are related to the surroundings plus the entropy of the surroundings and the change in entropy of the system. Then we also have these change in entropy of surroundings and system equal to the entropy of the universe. So now our change in delta G is related to the change in entropy of the universe, which is something that we talked about with spontaneity. So if a process is spontaneous, the change in entropy of the universe will increase, will be some positive number. So if our delta G is negative, that will actually give us a change in entropy of the universe that is positive, and our process will be spontaneous. So therefore, delta G, and specifically the sign of delta G, is linked to spontaneity. And then to spell this out very clearly, if we have a negative delta G, that reaction or that process is spontaneous at that particular given temperature. If we have a positive delta G, it is not spontaneous at that particular temperature. So let's go back to our water freezing example. Liquid going to solid. And using our free energy equation, so we don't have any specific numbers here, but we know the signs for a change in enthalpy, which was negative, and also the change in entropy, which was negative. So it turns out that we could get different possible signs for delta G. Sometimes delta G would be positive, non-spontaneous, and sometimes delta G would be negative, and it all depends on the temperature and maybe this term, the T delta S term. So if we have our delta H term is greater than our T delta S term, then we'll get a delta G that is negative. So the way that we would achieve this very small T delta S term is by having a low temperature. And for liquid going to solid, we know that it will happen spontaneously at a low temperature. So next, I would have the students do some practice questions about spontaneity and delta G. And the first one would be this, to work with the people around them to fill in this particular table. Thank you for your attention. Bye.